Hi everyone! In this video and in this chapter, we're going to be describing the relation between two variables. So in this section, we're going to look at scatter diagrams and the correlation. So first, let's talk about some things we've done in the past. Just a reminder, the mean of a variable, you get that by adding all the values of your variable and then dividing by the number of observations in your data set. So we've dealt with that quite a bit so far. The deviation about the mean, or how far like your data point deviates from the mean, and then how you find that is it's just the square root of the mean of the squared deviations about the mean. And then we've also talked about z-scores, and so a z-score represents the distance that a data value is from the mean, and we talk about that distance in terms of the number of standard deviations, like it's one standard deviation away from the mean, or 2 or 3 or so on. Okay, so something new, the response variable, since we're talking about two variables now, we have what's called a response variable, and it's a variable whose value can be explained by the value of the other variable, which we call the explanatory, or sometimes you hear it called the predictor variable. So we're going to have two variables in our data set, and one is an explanatory or independent variable, and then the other one is the response or dependent variable. The response variable depends on the explanatory, or the other way to say it is that the explanatory variable explains the response variable. So in research, we wish to determine how varying the amount of an explanatory variable, so if we vary that variable, affects the value of the response variable. Something else that we want to talk about before we get into the details of this section is confounding. So confounding in a study occurs when the effects of two or more explanatory variables are not separated. So therefore, any relation that may exist between an explanatory variable and the response variable may be due to some other variable or variables not accounted for in the study. So let's keep going a little bit and then I'll explain what I can about this. So a lurking variable is an explanatory variable that was not considered in the study, but that affects the value of the response variable in the study. In addition, lurking variables are typically related to any explanatory variables considered in the study. And then a confounding variable is also an explanatory variable that was considered in a study whose effect cannot be distinguished from a second explanatory variable. So an example of a confounding variable, let's say a teacher was trying to decide if online homework or textbook homework was better. And so if she taught in the morning, her morning class, she used online homework, and in the afternoon class, she used textbook homework, and at the end of the semester, she looked at the final exam scores. And let's say that the morning class did better. Well, a confounding variable would be the time of day. And the other variable, the explanatory variable, would be the type of homework. So we couldn't necessarily say that just because the students in the morning did online homework, that's why they did better. It's possible that the time of day that students chose to take the class said something about the student. Maybe they're more motivated in the morning. The difference between a lurking variable and a confounding variable is that the lurking variable is not considered in the study. So an example of a lurking variable, let's talk about another experiment or observation. Let's say the relationship between senior citizens that get a flu shot and their hospitalization rate. So there's been studies where it says that seniors that get the flu shots are less likely to be hospitalized for the flu. And so a lurking variable might be the age of the senior, or possibly the health status before they got the flu shot, or their mobility, how easily they can get around. So there's a lot of variables that could be affecting that study as well. And so these are all observational studies, and observational studies do not allow a researcher to claim causation, only association. So what this means is, in a study where you're just observing, like the classroom one or the flu shot example, you cannot say that something causes something else, like the flu shot causes less hospitalization, or online homework causes better grades. You can only claim association. So you could say less hospitalization is associated with the flu shot, things like that. And one of the reasons why we do observational studies as opposed to designed experiments is because it's more ethical a lot of the time. Okay, so now we're ready for our first objective. We are going to talk about scatter diagrams. So a scatter diagram is a graph that shows the relationship between two quantitative variables measured on the same individual. So each individual in the data set is represented by a point in the scatter diagram. So we're going to be plotting points. The explanatory variable is going to be plotted on the horizontal axis, and then the response variable is plotted on the vertical axis. This is similar to when you plotted points in algebra. Your input is represented on the horizontal axis, your output is represented on the vertical axis. So here's our example. A golf pro wants to investigate the relation between club head speed of a golf club and the distance that the ball will travel. He realizes other variables besides club head speed determine the distance a ball will travel, like the type of club you're using, the ball type, the person that's golfing, the weather, and so on. To eliminate the variability due to these variables, the pro uses a single model of club and ball, one golfer, and a clear 70-degree day with no wind. So he's eliminated a lot of the factors that could affect the outcomes by using one person to do this experiment, the same golf club and the same type of ball, and then picking a good day weather-wise. So this is the results in this table: club head speed, and then the distance that the ball traveled. So we're going to plot these points in our scatter diagram. And so our explanatory variable is going to be like the input, so it's these values here. And then our response variable here is going to be like our output, and we're going to plot those points. Okay, so here's our scatter diagram. Notice it's just points that we've plotted. So you can think of this as like the x-axis. This one is the y-axis, and you're just plotting points. So ordered pairs. So we had 99 as a club head speed, and the output was 258 for distance. So we plot that point right there. 100 for the club head speed corresponded to a distance of 257. So we plot that point. And we just do that for all the points in our table. And then it appears from our graph that as club head speed increases, the distance the ball travels increases as well. And we can see that visually because as the horizontal values increase, the vertical values are increasing. And it sort of has this trend of going upward toward the right. So it's not always clear which variable should be considered the response variable and which one we should consider to be the explanatory variable. Sometimes you just have to figure that out from the research that you're trying to, the research question. So scatter diagrams show the type of relation that exists between two variables. Our goal in interpreting scatter diagrams is to distinguish scatter diagrams that imply a linear relation, so think of a line, a nonlinear relation, so something that's not a line, or no relation at all. So here's some displays of various scatter diagrams and then the type of relation that's implied by the graph. So notice the first one, linear, because as the explanatory variable increased, so did the response variable, and you can sort of see that this always is making this like upward movement to the right. This looks like it's traveling in a line. Number 2 here is also a linear relationship, even though as the explanatory variable moves to the right, the response variable decreases. It's still linear because it's moving in a linear path like a line. Letter C here is nonlinear as well as D because it's not a line relationship, a linear relationship. As the explanatory variable increases, so does the response variable up until a point, and then the response variable starts decreasing. So this one's more rounded like that. Also D, nonlinear because it doesn't have a line or linear relationship. We go up with the explanatory and response, but then explanatory is still increasing, moving right, but the response variable is decreasing, but then it changes again. And then the last one, there's no relation here between the explanatory and the response variable because there's just this, like, kind of just looks like a patch of dots. There's no line or curve or anything associated with that. So just notice the differences. The data follow a linear pattern that slants either upward to the right or downward to the right in the first two. And then B and C are nonlinear, or sorry, C and D are nonlinear. And then E, there's no relation between the variables. So two variables that are linearly related are positively associated when above average values of one variable are associated with above average values of the other variable. And then below average values of one variable are associated with below average values of the other variable. Okay, that's a little bit wordy, but basically the two variables are positively associated. Whenever one variable increases, so does the other one. So when one variable goes up, gets larger, so does the other variable. We say that that's positively associated. And then two variables are linearly negatively associated if the opposite happens. So basically, if you just say that as one variable increases, the other one decreases, we say this relationship is negatively associated. Okay, now let's talk about the properties of the linear correlation coefficient. So a word of caution real quick. The horizontal and vertical scales of a scatter diagram should be set so that the scatter diagram does not mislead the reader. So make sure when you're drawing your scatter diagram, you scale the horizontal and vertical axis appropriately. Numerical summaries of bivariate, that just means two variables, bivariate data, should be used in addition to graphs to describe any relation that exists between two variables. So not just giving the graph as the only summary of the data, but numerical summaries as well. So now we're going to talk about what's called the linear correlation coefficient, or it's also called the Pearson product moment correlation coefficient, named after the mathematician Carl Pearson. And so basically what this is it's a measure of strength and direction. And it's of the linear relation between two quantitative variables. The Greek letter rho, it kind of looks like a P, but it's rho, represents the population correlation coefficient. And then R represents the sample coefficient, or correlation coefficient. What we're going to do is we're going to just look at the formula for the sample correlation coefficient. But just remember that it measures the strength and direction of the linear relation between the variables. So here's our sample linear correlation coefficient formula. So it kind of looks like a lot, but let's just talk about what's in this formula. So R was reserved for the sample, and then notice capital sigma just means you're adding, summation. So what we have in the parentheses here is x sub I minus x bar. Remember, x bar is just your mean. And then over s sub x, where s was our variable for standard deviation. Very similarly, we have that over here, but with y's. And then n came from the number in our sample. So the x sub I is just the ith observation. It could be like let's say 10th observation in our data set. We talked about the x bar is the mean, sample mean. And then s sub x is our standard deviation. The reason why we have y's also is because we have two variables. So the x's are reserved for our explanatory variable, and then we use the y's to talk about our response variable. So y sub I just means the ith observation. So it could be like the 13th observation of our data. Y bar is the sample mean of the response variable, and then s sub y is our standard deviation for that variable. And then like I said, n is just the number of our sample size. So here's an equivalent computation formula for our correlation coefficient. And so this one might be easier to work with to compute. I know it looks longer, but to do the computation, you don't normally ever have to do this by hand. You can use a technology to compute this. So here's some properties of the linear correlation coefficient. We're going to have 8 properties total. The coefficient is always between -1 and 1 to include that it can equal the endpoint. So it can equal -1, anything greater than that up until 1 to include 1. If r is equal to +1, then what we say is it's a perfect positive linear relation between the two variables. If it's equal to -1, we call that a perfect negative linear relation between the two variables. Pretty much these two things are true because, like, say it's +1, for every increase of 1 in our explanatory variable, then our response variable increases by 1 as well. Very much the same for the negatives. The closer r is to +1, the stronger the evidence is of a positive association between the two variables. And then very similarly with -1, the closer r is to -1, the stronger evidence we have that there's a negative association between the variables. If r is closer to 0, then what we actually can say is that there's little or no evidence that exists that the relationship is linear between the two variables. So r close to 0, it doesn't necessarily mean there's no relation, it just means there's no linear relation. So it can be one of our examples where our scatter diagram was curving. The linear correlation coefficient is unitless, and it measures association. And so the unit of measure for x and y actually play no role in interpreting r. So we don't have units on this number. And then last, the correlation coefficient is not resistant. So an observation that does not follow the overall pattern of the data could affect the value of this coefficient. If you remember resistant, a value was resistant if outliers didn't affect it. And so this is saying that it's not resistant. So something that's an extreme value could affect this correlation coefficient. Okay, so here's some examples of some scatter diagrams and then their linear correlation coefficient value. So notice in A, it's a perfect positive linear relationship because r is 1, and basically for every 1 incremental increase in the explanatory variable, the response variable increases by 1 as well. That's why you get this nice line that has this increase of 1. And over here, very much the same, but negative. So a perfect negative linear relation, r is -1. When the explanatory variable decreases by 1, or sorry, increases by 1, the response variable is decreasing by 1. We have in part B and part E, strong positive and negative linear relations. So it's not exactly this perfect relation, but it is very strong. R is about 0.9 or -9 in these two. And then we have in C and F moderate linear relations. So this one's positive, this one's negative. And notice the data is a little more scattered about, but it is still increasing together toward the right. R is about 0.4 here, R is about -4 here. The data is looking like it's decreasing to the right. And then in G, there's no linear relation at all, so R is close to 0 here. And then similarly on H, there's no linear relationship here, so R is also close to 0. So computationally, kind of what's going on here is if you use your means, your x mean and your y mean, to separate your data into quadrants here, then what you get is 4 quadrants. We go counterclockwise, so quadrant 1, 2, 3, and 4. And just mathematically, if you think about it, over here, anything to the right or more than the x mean is going to be positive. And then anything above or larger than the y mean is going to be positive as well. So basically these values are positive, so when you multiply them, you're going to get a positive number. Down here in quadrant 3, anything less than or to the left of the x mean is negative, but also anything below or less than the y mean is also negative. So here you're going to get negatives, two negatives that multiply, which turns positive as well. So when you add these up, this is going to give you a positive correlation coefficient, because these are both going to be positive values when you do their product. So if we think back to G on our example here, this one had an R value close to 0. And if you divide or separate the region into 4 quadrants, like let's say our X bar was here. Sorry, it's not a very straight line, but let's say that's X bar. And then let's say that Y bar's here. Pretend it's straight. And so this is quadrant 1, 2, 3, and 4. And so what's happening is your values are equally negative and positive. Everything's positive here when you multiply. Everything's positive here when you multiply. But then in quadrants 2 and 4, everything's negative here and here when you multiply. And so all that kind of combines and adds up to give you 0. So anytime the data is like equally dispersed about the 4 quadrants, then our linear correlation coefficient is close to 0. So just a little bit of mathematical reasoning for the R values. So next, let's compute and interpret the linear correlation coefficient. So in this table, we're going to compute the linear correlation coefficient for this data. The scatter diagram of the data is shown here, and our dashed lines are given for our mean of x and our mean of y. So we have just a few input points. So 1, 18, we plot that point right here. 3, 13 is plotted here, and so on with all of our data values. And so just based on the visual, if you take a look at it, let's see if you can understand what's the relationship here. So let's compute it and see if our math works out with what we thought visually. So the mean for x, the average for x is 4. The standard deviation is about 2.4. The mean for y is 10, and the standard deviation for y is about 5.6. So we've computed all these in the past. You can use technology to compute these, or you can use the formulas. There wasn't a lot of data points, so we could do this one by hand. So next, our columns 1 and 2 of our table contain the data from our original table. And then what we want to do to figure out our correlation coefficient, and notice we're doing this by hand, but in the future you can use technology. We're finding out 2 values ahead of time, and then we're going to multiply. So we're just, for each of our data points, we're taking that x number minus the mean, dividing by the standard deviation. That's why for the first one, we would have 1 minus 2.44949 over, 1 minus 4, because that's x bar, 1 minus 4 over 2.44949. And we would do that for each of them, for x. We would do the same thing for y. So for example, the first one would be 18 minus 10 divided by 5.612486. And that's how we get these numbers here. Now, for our correlation coefficient computation, we want to multiply those. So in the last column here, we've multiplied them. And so that's going to give us our third column. And then when we add those up, if you remember our formula, we wanted the summation of this product. So when we add those up, we get this negative 3.7824. And then last, we want to divide by n minus 1. So our sample had 5 observations. So we're going to divide this number by 4 to get our correlation coefficient value of negative 0.946. We're going to just agree to round to 3 decimal places. And so this number here suggests a strong negative association between the 2 variables. And if you look back at our scatter diagram, it was looking like the variables were going down to the right. So as the explanatory variable increased, the response variable decreased and this number is also, it confirms that. So now we're going to use some technology. I'm specifically going to use Excel, and we're going to get the scatter plot and then calculate the correlation coefficient. Okay, so I've entered the data for our table here and in Excel, and the first thing I'm going to do is get the scatter plot. So I'm going to go over to Insert, and notice right here is scatter plots. So let's go ahead and highlight our cells, and I'm going to pick this, the first one, and there it is. So it generated our scatter plot for us. We can adjust anything that we need to, maybe the Y values or so on, but this is a pretty good scaling, and then I can retitle this chart. Now the correlation coefficient calculation, we can do that a couple of ways. So first I'm going to use a formula. So just to show you where it's at, under formulas, it's going to be more functions, statistical, and it's this one here, coral. So the correlation coefficient. So my array 1, I'm going to highlight my explanatory variable column. Array 2 is going to be my response variable column. And okay, and there it is. So there's my correlation coefficient calculated with technology instead of by hand. Let me do it one more time using our data analysis tool pack. So under data, I'm going to do data analysis, and I'm going to click on correlation and hit OK. And I already highlighted those, but let me just go ahead and say it's this information, and we're just going to output it. Let's put it right here. Well, let's see. Click here and output it here. Okay, and there it is. So same value. So that's how we can do our correlation coefficient calculation using Excel. The next thing we're going to do is to determine whether a linear relation exists between two variables. So here's a test to figure this out. Step 1, determine the absolute value of the correlation coefficient. Basically means if it's negative, just take the positive value. Step 2, find the critical value in Table 2 from Appendix A, which I'm going to give that to you, for the given sample size. And then Step 3, if the absolute value of the correlation coefficient is greater than the critical value, which is what we find from the table, then a linear relation exists between the two variables. Otherwise, no linear relation exists. Okay, so here is Appendix A, Table 2. And so in the left column, we have our sample size. And on the right column, we have what's called a critical value. So if we follow our steps for determining a linear relation, we take the absolute value of our correlation coefficient, and we compare it to this critical value number in the right column, and then see which one's greater. So if the correlation coefficient is positive and then greater than the critical value, the variables are positively associated. If the correlation coefficient is negative and less than the opposite of the critical value, basically if we put the minus sign on the critical value, then the variables are negatively associated. So here's just a visual for that statement. Remember, the closer we are to 0 with our correlation coefficient value, there's no linear relation, but the closer we are to -1 and 1, there's the positive or negative linear association. Now, does a linear relation exist? We're going to use the results from a previous example, the one with the club head speed and distance, to figure out if we have a linear relation. So if we calculate the linear correlation coefficient between our explanatory variable, club head speed, and our response variable, distance, we calculate 0.939. And that's already positive, so the absolute value is the same number. And then we go to our table 2 to find a critical value for a sample size of 8, because we had a sample size of 8 from that experiment. And the corresponding critical value is 0.707 from our table. Then we just compare these two. Because our correlation coefficient is greater than the critical value, a positive association or positive linear relation exists between club head speed and distance. And if you remember our scatter diagram, we could tell visually that we had this positive linear relation. Our last objective, we want to explain the difference between correlation and causation. So if data used in a study are observational, we can't conclude two correlated variables have a causal relationship. Remember, we talked about this. We can only talk about association for our observational studies. So we mentioned this, but a lurking variable is related to both the explanatory variable and the response variable. So for an example, as air conditioning bills increase, so does the crime rate. So the question would be, does this mean that folks should turn off their air conditioners so that crime rates decrease? Well, definitely not. In this case, the lurking variable is air temperature. As temperatures rise outside, air conditioning bills go up, and so does crime rates. So let's take a look at this example here. Because colas tend to replace healthier beverages, and colas contain caffeine and phosphoric acid, researchers wanted to know whether cola consumption is associated with lower bone mineral density in women. So we have a table here that lists the typical number of cans of cola consumed in a week and the femoral neck bone mineral density for a sample of 15 women. And then the data was collected through a prospective cohort study. So the number of cans of cola per week consumed and the corresponding bone mineral density. So here's our scatter diagram for our data. The correlation between the number of colas per week and bone mineral density is negative 0.806. So notice this is fairly close to negative 1. The critical value for correlation with sample size of 15, if we go to our table 2, the critical value is 0.514. So if we take the absolute value of our correlation coefficient, 0.08 is greater than our critical value of 0.514. So we conclude that there is a negative linear relationship between the number of colas consumed and bone mineral density. Remember, negative linear relationship just means that the relationship is linear, but it's negative, meaning as one goes up, the other goes down. So this is saying as the number of cans of cola consumed goes up, the bone density, bone mineral density goes down. And you can tell, so we did it with our values here, but you can tell kind of visually from our scatter plot that that's true. So can the authors conclude that an increase in the number of colas consumed causes a decrease in bone mineral density? So be careful with that word cause. Identify some lurking variables in the study. In prospective cohort studies, which this one was, data are collected on a group of subjects through questionnaires and surveys over time. Therefore, the data are observational. So this was an observational study as opposed to a designed experiment. So the researchers cannot claim that an increased cola consumption causes a decrease in bone mineral density. So in their article, the authors actually identified a number of lurking variables that could confound the results. Some of the ones they came up with was the age of the women, body mass index, their height, whether or not they smoked, alcohol intake, their calcium levels, caffeine, and so much more. So a lot of lurking variables that could have affected the bone mineral density. So the authors were careful to say that increased cola consumption is associated, so that's the key, associated with lower bone mineral density because of potential lurking variables. They never actually stated that increased cola consumption causes lower bone mineral density. So it's just a difference between cause and association. All right, thanks for watching. That's it for this one.